This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas.
Okay, so imagine this, just for a second. You're standing on some alien world. The ground under your feet is, I don't know, sandy, maybe a little warm. And you look up, you shield your eyes from the glare, and setting over these, like, alien dunes, you don't see one sun.
You see two.
You see two.
The double sunset.
The double sunset. It's so iconic. It's the whole Tatooine fantasy, right?
Oh, absolutely. I mean, it is probably one of the most powerful, most enduring images in all of science fiction. It just screams, this is not Earth.
It does, and it feels so plausible. You know, we're in a galaxy with just hundreds of billions of stars. And we know for a fact that binary star systems, these pairs of stars locked in a gravitational dance, are super common.
Incredibly common. You could even make the argument they're more common than single stars like our sun.
So we're the weird ones.
In a way, yeah. Single stars are kind of the exception, not the rule. Most stars are born with a buddy.
So logic would just tell you there have to be planets out there where you'd have two shadows, where day and night is this complicated, beautiful mess of orbital mechanics.
Right. Imagine a red dwarf and a yellow sun, and you get these, like, purple twilights. It's a really romantic idea.
It is. And for a long, long time, astronomers thought it was way more than just a fantasy. The scientific expectation, the default assumption really was that planets forming around two stars.
What we call circumbinary planets, or CBPs?
Right, CBPs. That they should be, pretty common. I mean, there's no big law of physics that says no planet construction allowed here.
Not at all. Gravity is gravity. The basic recipe should hold up. You get dust, it clumps into pebbles. Pebbles make rocks. Rocks make planetesimals. And, eventually you get a planet.
The kitchen might be a bit more chaotic with two giant fusion reactors in the middle, but you should still be able to bake a cake.
That's the theory. The whole process of accretion, of building up matter, it should work. It might be a little harder, but it shouldn't be impossible.
But then, reality.
And a space telescope named Kepler.
And this is where our deep dive starts today. We're looking at a really fascinating new paper, and a few others that led up to it. The main one is called, and I love this, Apsidal resonance.
It does sound a little clinical.
It sounds like something your mechanic would tell you is wrong with your car.
Yeah, sorry, mate, your Apsidal resonance is shot. That's going to cost you.
Exactly. But despite the name, what this paper is really doing is investigating a cosmic crime scene. It's a genuine murder mystery.
The victims are missing planets that, by all rights, should be there, and they've just vanished.
And the story this paper tells is one of gravity, of this thing called resonance, and a mechanism that basically acts like a cosmic broom, just sweeping entire solar systems clean.
But before we get to the how, the weapon, we really need to understand the scale of the crime. We have to look at the missing persons report.
Let's do it. Let's hit the stats, because when I was reading the source notes for this, they're kind of staggering. The Kepler mission, for anyone who doesn't know, was our premier planet hunting telescope.
It just stared, unblinking, at one patch of the sky for years.
Just looking for those tiny, tiny dips in a star's light that tell you a planet just crossed in front of it.
And in that field of view, Kepler found about 3,000 eclipsing binaries.
Okay, let's define that really quick. An eclipsing binary, or EB, is the pair of stars orbiting each other that, from where we are on Earth, they pass in front of each other.
Yeah, the orbit is edge-on to us, so they eclipse each other.
Which is the absolute perfect setup for finding planets, isn't it? Because if the stars are lined up flat with us,
then the disk of gas and dust they form from should also be flat to us.
Meaning any planets that formed in that disk should also be orbiting on that same flat plane.
Exactly. We should see them transit. The geometry is basically handed to us on a silver platter. It takes away the whole, maybe we're just looking from the wrong angle problem. We know we have the right angle.
So, 3,000 perfect edge-on systems primed for planet detection. How many transiting circumbinary planets did we find?
Go on.
I had to double-check this number because I thought it was a typo. The number of confirmed planets is about 14.
14.
4 out of 3,000.
It's statistically baffling. It's nothing.
It's a rounding error. I mean, even if you're generous and you throw in the whole maybe pile, the unconfirmed candidates, you only get to, what, 47 total?
It's a tiny, tiny fraction of what we expected. It's so low, it makes you question the fundamental assumption that planet formation is, robust around binary stars.
It's not just, oh, they're a bit rare. It's where is everybody?
It's the Fermi paradox for Tatooines.
But it gets weirder. If you dig into the data, the mystery gets even more specific. It's not just that the numbers are low everywhere. They're basically zero in one very specific place.
The CBT desert.
The circumbinary planet desert. So what are the borders of this desert? Where is this emptiness?
So a lot of the binaries Kepler found are what we'd call tight binaries.
Tight meaning close together.
Very close. They are whipping around each other incredibly fast. We're talking about orbital periods of less than, say, 7 days.
Wait. So a year for these two stars, one full orbit, is less than a week.
Yeah. Sometimes just 2 or 3 days. Imagine 2 stars, maybe each the size of our sun, spinning around a common point so fast their whole dance is over between Monday and Friday.
They are practically touching.
They're very, very close. And in that group, all those binaries with periods under 7 days, we have found pretty much 0 planets.
0.
The shortest period binary that we know has a planet is a system called Kepler 47, and its period is 7.45 days, just over the line.
So if your two suns orbit each other in 8 days, you might have planets. If they orbit in 6 days, you've got nothing.
Nothing. It's not a gentle slope, it's a cliff edge. Below 7 days, it's a graveyard.
So that's the mission for this deep dive.
Yeah.
Why? Why is a Tatooine fantasy a bust if the suns are too close? What is killing all these planets?
And this new paper, it argues it's not that the planets never formed.
It's that they were destroyed.
Wiped out by a dynamical twist.
I love a good cosmic destruction story. But, okay, before we get to the weapon, we have to set the scene. The scene of the crime. We need to really understand the environment these planets are born into.
Right. It's not a calm place to grow up.
So picture it for us. A protoplanetary disk. A giant flat pancake of gas and dust.
In our solar system, it was all swirling around one central point, the protosun. But here, the center isn't a point. It's 2 stars doing a waltz.
A very fast waltz.
A very fast waltz. And right up close to those stars, the gravity is just, it's chaos.
How so?
You've got 2 massive objects tugging on everything, and they're constantly changing position relative to each other. The gravitational field is being churned up. We call this the instability zone.
Instability zone. It sounds dangerous.
It is if you're a planet trying to form. You couldn't build a planet there. The gravitational forces, the shear, would just rip any clumps of rock apart.
It's like trying to build a house of cards inside a running washing machine.
That is a perfect analogy. So that's the no construction zone. But if you go further out in the disk,
Things calm down.
things calm down a lot. Far enough away, the gravity of the 2 stars starts to feel like the gravity of one single, more massive star. It's stable, it's peaceful. That's where you build your planets.
Okay, so the planet is born out in the quiet suburbs of the solar system. But we know that planets don't just stay put. They like to move.
They migrate. It's a natural part of the process. As the planet gets bigger, it interacts with all the gas and dust still left in the disk. It creates these waves, and the waves push back on the planet.
And that makes it spiral inward.
It loses a bit of angular momentum and spirals in, moving from the suburbs toward the chaotic city center.
And standard theory says it should migrate inward until it gets close to that instability zone.
And then it should stop. It parks itself right on the edge. The gravity from the binary clears out the gas in the very center, so the force that was pushing the planet inward just disappears. The migration engine shuts off.
So if the planet forms far out, moves in, and then parks itself at a safe distance, we should see them. Even around these tight binaries, they should be all lined up, parked right at the edge of that 7-day cliff.
We should. All our models, all our simulations of planet formation, they suggest there should be a pileup of planets right at that stability limit.
And that's the core of the puzzle. Look at the parking lot, and it's completely empty.
So, of course, astronomers have had ideas about this for a while. It's not like this is a brand new mystery.
Right. What were the usual suspects, the leading theories before this new paper came along?
Well, the simplest one was just observational bias.
We just missed them.
Yeah, I mean, these tight binaries are messy. They spin really fast. They have huge star spots. They flare. Their light is naturally very flickery. So maybe the tiny dip from a transiting planet just gets lost in all that noise.
Which seems plausible. Trying to find a planet is like trying to spot a gnat flying in front of a searchlight from a mile away. If the searchlight is flickering on and off.
It becomes almost impossible. So that was one idea. plausible, but probably not enough to explain the complete absence of planets. Our data analysis techniques are really good.
Okay, what else?
Another idea was interference from a third star.
Like a distant cousin meddling in the marriage.
Exactly. Something called Kozai-Ladov cycles. If you have a third star orbiting the binary on a tilted, distant path, its gravity can exert this long, slow tug that messes up the inner system and could kick planets out.
Or maybe the disk itself is the problem. Maybe that washing machine effect is bigger than we thought, and it's just too turbulent to even form planets in the first place.
That was another suspect. But the authors of this new paper, they argue that none of these are the full picture. They say there's a killer hiding in plain sight, in the physics of the star's orbits themselves.
The killer we overlooked because it involves a force we usually think of as, well, pretty subtle.
General relativity.
And to understand how it works, we have to talk about the weapon. We have to talk about Apsidal precession.
Yes, Apsidal precession.
Okay, break this down for me. I want the conceptual visual. No equations. I'm driving my car right now. What should I be picturing in my head?
Okay, picture a hula hoop.
Got it. A classic plastic one.
You're spinning it around your waist. Now, the shape of that hoop as it goes around you, it's not a perfect circle, right? It's an ellipse. It has a long axis and a short axis.
Right. It gets a little stretched out.
Now, imagine that while that hoop is spinning around you, the whole oval shape itself is also slowly rotating.
Oh, okay. So the long part of the oval isn't always pointing, say, north. It's turning, like a spirograph pattern.
Exactly like a spirograph. That slow rotation of the orbit's orientation. That's precession. The orbit isn't a fixed track. It's a track that is constantly swiveling around.
Okay, I think I've got that. So in our binary system, who's doing this swiveling?
Well, we have two main players. First, the two binary stars themselves. Their mutual orbit around each other precesses. It wobbles.
What makes the star's orbit wobble?
Two main things. The first one is tidal forces. Because the stars are so close, they're not perfect spheres. They pull on each other and stretch each other into slightly egg-like shapes.
So they're squishing each other.
They're squishing each other, and that makes the gravitational field slightly non-uniform, which in turn makes the whole orbit slowly rotate.
Okay. And the second reason?
This is the big one. General relativity. Einstein's gravity.
And usually when we talk about GR in solar systems, it's this tiny, almost imperceptible effect.
Usually, yes. In our solar system, Newton's laws are, 99.99% of the story. But when you have two massive stars really close together, whipping around each other, the curvature of space-time itself becomes significant.
And that makes the orbit wobble.
It makes it precess, and it does so much faster than Newton's laws would predict.
So the inner stars are wobbling. What about the planet?
The planet, which is orbiting further out, is also precessing. Its orbit is also a hula hoop. The constant gravitational tugging from the two inner stars makes the planet's orbit wobble too. It has its own separate precession rate.
Okay, so we have two hula hoops. An inner one for the stars and an outer one for the planet.
Yeah.
And both are slowly turning, like two spirographs.
And this is where we get to the heart of the mechanism, the resonance condition, the lock.
The lock. This sounds like the critical moment in a heist movie.
It kind of is. Resonance is a word we use in physics when two things are vibrating or oscillating at just the right frequencies.
And in this case, the resonance happens when the rate of the binaries wobble matches the rate of the planet's wobble.
They sync up.
The two hula hoops start turning at exactly the same speed.
Exactly. It's like a dance. Suddenly, the inner stars and the outer planet are shifting their orbits in perfect unison.
And I know enough about physics to know that when you hit a resonance, big things happen.
Huge things happen. It's the most efficient way to transfer energy into a system. Think about pushing a child on a swing. If you push at random times, you don't accomplish much. But if you push at the exact right moment in the swing cycle, at its resonant frequency, the swing goes higher and higher with just a tiny bit of effort. You're pumping energy into it.
So in these systems, the binaries wobble can pump energy into the planet's orbit when they match up.
And that match, that resonance, that's the trap.
Why a trap? Why doesn't it just happen for a moment and then they fall out of sync again, the frequencies just cross and move on?
Because the system isn't static. It's evolving over time. And this is the great narrative arc of this paper, a process they call the sweeping.
The sweeping. Okay, lay it out for me.
All right. So binary stars don't usually start out super tight. When they're young, they might be orbiting each other every, say, 20 or 30 days. But over millions, even billions of years, that orbit shrinks.
They spiral in toward each other. Why?
Yeah.
Are they losing energy somehow?
Yes. The main mechanism is called tidal decay. We just talked about how they raise tides on each other, stretching each other out. Well, that sloshing of material inside the stars creates friction, which generates heat. And that heat has to come from somewhere. It comes from the orbital energy of the system,
So they're literally bleeding orbital energy away as heat.
which causes them to fall closer together. The orbit tightens.
So the binaries year is getting shorter and shorter over cosmic time.
Exactly. Now think back to what we said about general relativity.
That its effect gets stronger when things are closer and more massive.
Bingo. So as the stars spiral closer together, their GR-driven precession gets faster and faster.
The wobble speeds up.
It's like someone is slowly turning up the speed on a cosmic turntable. The frequency of the binary's precession is steadily increasing.
And the planet is just sitting out there minding its own business with its own natural wobble frequency.
Yes, and as the binary's frequency sweeps upwards, eventually, click, it matches the planet's frequency.
And that's the capture. Resonance.
That's the capture. But here's the truly insidious part. The binary doesn't stop shrinking. The tides keep pulling energy out, so its precession keeps getting faster.
Okay.
But because the planet is now locked in resonance, the binary drags the planet's frequency along with it.
It refuses to let go.
It refuses to let go. It forces the planet to keep up. But the only way the planet's orbit can precess faster and faster to stay in that lockstep is to change its shape. The planet has to pay a price.
And what's the price?
Eccentricity.
The orbit has to get more stretched out.
It gets pumped. The resonance takes energy from the binary's shrinking orbit and pumps it directly into the planet's orbital shape. It goes from a nice, nearly circular orbit to a long, stretched-out, dangerous oval.
So let me see if I have this visual right. You've got the two stars spiraling inward, getting tighter and faster. And as they do, they grab onto this planet with an invisible gravitational tether.
A resonant tether.
And they just start stretching its orbit out like a rubber band.
That's a perfect way to put it. To keep its wobble synchronized with the ever-faster binary, the planet must become more eccentric. And we're not talking about a small change. The simulations show this is a catastrophic process.
So let's talk about those simulations, because this isn't just a theory on a blackboard. The researchers tested this. They ran a massive digital experiment.
They did. They took real data from something called the Villanova Kepler catalog. That's a database of 1,630 actual binary systems that Kepler observed.
So real star systems that are out there in our galaxy right now.
Exactly. And for each one, they basically wound the clock backwards. They said, okay, this binary has a period of, say, 3 days now. Let's simulate it starting out with a 20-day period and let it spiral in over billions of years due to tides.
And then they just dropped a planet in there to see what would happen.
They populated these evolving systems with test planets at various distances and hit the play button on their universe simulator to watch the chaos unfold.
I'm looking at one of the main plots from the paper, figure 6. They call it the red mushroom, and you can immediately see why.
It's a really powerful visualization. It tells the whole story in one image.
So for everyone listening, picture a graph. The bottom axis is the binary's orbital period, so wide is on the right and tight is on the left. The vertical axis is the planet's eccentricity, how stretched its orbit is. And on the right side of the graph, where the binaries are wide, with periods of 10, 20, 30 days, you see a bunch of green dots sitting at the bottom.
Those are happy, stable planets on nice circular orbits, low eccentricity. They're just chilling.
But as your eye moves to the left, towards the tighter and tighter binaries, all of a sudden, it just explodes upwards. You get this massive cloud of red and yellow points shooting up to incredibly high eccentricities.
It looks exactly like a mushroom cloud.
And that mushroom cloud, that's the massacre.
That's the massacre. The results from the simulations were just devastatingly clear. They found that 8 out of 10 planets placed in these systems will encounter this sweeping resonance.
80%. So this isn't some rare, freaky occurrence. This is standard operating procedure for a tight binary system.
It's the default path. And of those 80% that get caught in the resonance, 3 out of 4 of them are completely destroyed.
Destroyed. That feels like a really strong word for astronomy. We usually hear things like disrupted or perturbed. What does destroyed actually mean here?
It means one of 2 very final outcomes. The first is engulfment.
As in eaten by the stars.
Pretty much. The resonance pumps the orbit so eccentric, so stretched out that its closest approach, the periapse, gets dragged right into that chaotic instability zone we talked about at the beginning.
So it either hits one of the stars directly?
Or it gets so close that the tidal forces from the two stars just shred it into pieces. A fiery, messy end.
Okay, that's one way to go. What's the other?
Ejection. The resonance pumps so much energy into the orbit, makes it so wild and unstable that the planet just gets completely kicked out of the system.
Blowing out into deep space.
It becomes a rogue planet, a frozen orphan untethered from its suns, doomed to wander the dark between the stars forever.
So, the very same process that makes a binary tight, this slow tidal decay, is the exact same process that cleans out all the planets.
It's a self-cleansing mechanism. It perfectly, beautifully explains the CBP desert. The reason we don't see planets around binaries with periods under 7 days is because this resonance swept through and either ate them or threw them out billions of years ago.
The desert isn't a place where nothing could grow. It's a place that was scoured clean.
It's a graveyard.
But wait a minute, you said 3 out of 4 are destroyed,
I did.
which implies that 1 out of 4 survives.
Some do. And this gets us into what the paper calls the survivors and the detectability paradox.
Ooh, I love a good paradox. So who are the survivors? What makes them special? Are they just tougher?
It's more about location, location, location. The researchers identified a few different categories or regimes of survival. First up, you have Regime A. These are the uncaptured.
The lucky ones.
Basically, these are planets that were just orbiting too far away from the binary. The resonance sweep, as the binary tightened, just never reached them. It's like a wave that runs out of steam before it gets to you on the beach.
So they never got the invitation to the destructive dance.
They never did. And they are left on their nice, stable, circular orbits. Those are the green dots in the plot.
Okay, so some just missed the bullet entirely. Who else survives?
Then you have Regime G, the escapees.
How do you escape? I thought you said it was a lock, a trap.
It is a lock, but sometimes, in the chaos of these systems, you can pick the lock. A planet might get caught in the resonance, its eccentricity starts to get pumped up, it gets shaken around. But then due to other smaller perturbations, the geometry shifts just enough that the lock breaks. It falls out of resonance.
So it gets away but not unscathed. It's left with a scar.
A permanent scar, yes. It's left with a moderately eccentric orbit. It's moving in an oval now, but not a life-threatening one. It survived the encounter, but it's been altered.
And then there was a third group, the yellow survivors.
Oh, yes, these are maybe the most interesting ones. These are planets that get caught, they get locked, and their orbits get pumped to extreme eccentricities. We're talking 0.6, 0.7, 0.8. Really stretched out.
That sounds like they should be destroyed.
They are living right on the edge of destruction, but they just happen to be orbiting far enough away that even with that incredibly stretched out orbit, their closest approach doesn't quite dip into the instability zone.
So they're just skimming the surface of the fire on every single pass.
On every single orbit for billions of years. A very precarious existence.
But this brings us to the paradox.
Yeah.
If these survivors exist, the distant peaceful ones, the scarred escapees, the daredevils, why don't we see them? Why is the desert still a desert in Kepler's data?
Right. If there are survivors, show us the survivors.
Exactly.
To understand that, you have to think about the geometry of how we find planets in the first place.
With transits, waiting for them to pass in front of their star.
And the probability of seeing a transit, of having everything line up just perfectly from our point of view, depends heavily on how far the planet is from its star.
It's basic geometry. If I have a flashlight and a marble,
If the marble is right up next to the flashlight bulb, it's really easy to make it block the light. The target is huge. But if that marble is 50 feet away,
the alignment has to be absolutely perfect down to a fraction of a degree for it to pass in front of the bulb from my perspective. The chances are way, way lower.
drastically lower. So where are most of the survivors in these simulations?
They're the ones orbiting far away.
Exactly. The ones close enough to be easily detectable were the first ones to be destroyed by the resonance. The survivors are overwhelmingly on wide, distant orbits.
So geometrically, they're basically invisible to a survey like Kepler.
Precisely. Kepler stared for 4 years. For a planet orbiting that far out, it might only have 1 or 2 transits in that entire time, and the probability of us being aligned to see even one of those is tiny.
So the desert isn't actually empty. It's just that the front row seats are all empty because those planets got killed, and the survivors are all hiding way up in the nosebleed section where we can't see them.
That's the paradox. The very mechanism that lets them survive, being far away, also makes them nearly impossible for us to detect with our current methods. The resonance cleared the front yard, but the backyard could still be full of planets. We just can't see over the fence yet.
That is such an elegant and kind of tragic solution. It just paints this completely different picture. We're not looking at a barren wasteland. We're looking at a ghost town where the only inhabitants are hiding in the hills.
It also gets really interesting when you dig into the intellectual history of this idea. This is where we get into the real deep dive analysis of the paper.
Right. There was a quote in there that completely surprised me from the writer Jorge Luis Borges.
Borges, the Argentine writer of, magical realism, The Library of Babel, showing up in a dense astrophysics paper.
Yeah. You don't see that every day. The quote was, "Each writer creates his precursors."
Each writer creates his precursors. It's such a profound idea.
What does it mean in this context? How does an astrophysics paper create its own precursors?
It means that a new discovery, a new synthesis like this, fundamentally changes how you read the scientific literature of the past. Suddenly, older papers that might have seemed disconnected or like they only had a small piece of the puzzle now look like prophetic stepping stones.
So this new, complete theory of apsidal resonance sweeping makes us look back at older research in a new light.
It does. The authors of the paper specifically point to earlier work by scientists like Migazewski and Marteling. And these people, years ago, they saw parts of this. They knew general relativity was important for binary orbits. They knew about resonances. But they hadn't quite put together this grand narrative of the tidal decay sweeping the resonance across the system and causing this mass extinction event.
It's like they had all the clues in the mystery novel, the candlestick, the rope, the lead pipe, but they hadn't quite figured out that it was Colonel Mustard in the library.
That's a great way to put it. And now, looking back through the lens of this new paper, we can say, look at that. They were so close. They were the precursors. It's a really lovely and honest acknowledgement of how science actually works. It's not just one genius having a eureka moment.
It's about recontextualizing what we already knew.
We stand on the shoulders of giants, but sometimes a new idea is the telescope that lets us finally see what those giants were pointing at.
There's another huge piece of this that I found so fascinating. It's a deep irony about the role of general relativity, and it involves our own solar system, specifically the planet Mercury.
Oh, yeah. The irony of general relativity. This is my favorite part of the whole story.
So in our solar system, Mercury is the closest planet to the sun.
Yeah.
And its orbit precesses, it wobbles.
It does,
Right.
famously so. In fact, explaining that wobble was one of the very first major triumphs of Einstein's theory. Newton's laws couldn't quite account for it. There was this tiny discrepancy. Einstein's theory of curved space-time nailed it perfectly.
But GR does something else for Mercury, something
Yeah.
protective, right?
In our solar system, general relativity is a stabilizer. It's a force for good, you could say.
How so?
If gravity was purely Newtonian, the various orbital resonances between Mercury and, say, Jupiter would be slightly different. And simulations showed that without GR, there's a non-trivial chance that over billions of years, Mercury's orbit could become chaotic.
Chaotic as in?
As in crashing into Venus or falling into the sun or even getting ejected from the solar system. GR's subtle effects actually detune the most dangerous resonances. It keeps the frequencies from locking up.
So in our house, GR is the shield. It's the guardian angel that keeps Mercury safe.
Exactly. It prevents the lock.
Yeah.
But in these tight binary star systems,
CR is the weapon.
it's the agent of chaos. It's the very thing that drives the binaries' precession faster, that tunes the resonance, that creates the lock that destroys the planet.
That is just, it's a wild duality. The exact same fundamental law of the universe can be a protector in one system and a destroyer in another.
It's all about the architecture. One sun, GR saves you. Two suns too close together, GR might be what kills you.
It's one of those aha moments that really makes you appreciate how complex these systems are. Physics isn't just a simple set of rules. Context is everything.
It really is.
So looking forward, what does this mean for the future? We focused on tides shrinking the binary orbit. But the paper mentions other mechanisms too, something called magnetic braking.
Right. So we've established that tidal decay is this slow, powerful force that shrinks binaries. But it works best when the stars are already pretty close. There's another process, magnetic braking, that can take over and make things even tighter.
How does that work? Is it literally like hitting the brakes?
In a way. Imagine these stars have powerful magnetic fields, and they're constantly blowing off a solar wind, a stream of charged particles.
Okay.
The magnetic field lines extend out into space, and they grab onto this wind and sort of co-rotate with it for a while before letting go. It's like a spinning figure skater extending her arms. It flings mass away, and that carries away angular momentum.
And that acts as a brake on the star's spin.
It slows the spin down. And in a tight binary where spin and orbit are linked, slowing the spin forces the orbit to lose energy and shrink even further.
So it's another way to tighten the noose.
And it's particularly effective for very, very tight binaries. We're talking sub-day periods, stars that orbit each other in a matter of hours.
Complete speed demons.
And the paper makes the prediction that this same resonance sweeping mechanism works there too. It acts as a mop.
A mop, I like that.
If the tidal decay phase was the broom that swept out most of the planets, magnetic braking is the mop that comes in afterward to clean up any survivors that might have been missed. It ensures that the very tightest binaries are almost certainly barren.
It's just relentless. The universe seems determined to scrub these systems clean.
It does, but there's a little glimmer of a different outcome, a variation on the theme. We talked earlier about how planets migrate inward through the disk.
Right, coming in from the suburbs.
Well, what if the planet migrates inward while the binary's orbit is stable and not changing much? In that case, the resonance crossing happens in the opposite direction.
What do you mean, the opposite direction?
Remember, in the destruction scenario, the slow wobbling planet gets caught by the fast wobbling binary as the binary speeds up.
Okay.
In this migration scenario, the binary's wobble speed is fixed, and the planet, as it moves inward, is the one whose wobble speed changes, sweeping past the binary's frequency.
So they cross paths, but they don't lock on.
Exactly. It's too quick an interaction. There's no time for a capture. Instead of a prolonged energy pumping trap, it just delivers a kick.
A kick?
The planet feels a sudden gravitational jolt as it passes through the resonance. It gets a sudden kick of eccentricity. A permanent wobble is imparted to its orbit. But it survives. It passes right through and keeps on migrating.
So if you're a planet in one of these systems, your survival strategy is to be the one on the move, not the stars.
That seems to be the way to do it. Be proactive in your migration.
This has been an incredible narrative. We started with this beautiful, romantic fantasy of a double sunset on Tatooine. And we've ended up in a cosmic graveyard, a story of gravitational murder on a galactic scale.
It's a bit of a somber verdict, but it's a powerful one. The CBP desert is real, and it's most likely a graveyard. It's not empty because planets couldn't form there. It's empty because they were systematically destroyed or evicted.
From a calm, dusty disk to a deadly, resonant dance driven by the stars themselves shrinking, it really does change how you look up at the night sky. You see those little pairs of stars and you just wonder.
What did you do? What did you devour?
So before we wrap this up, I want to leave our listeners with one last provocative thought. It's something the paper just hints at, but it really stuck with me. It's about that invisibility paradox we talked about.
Okay, go for it.
We established that the survivors are hard to see because they're far away. But you would think that if a planet is on a really eccentric orbit, swinging in close and then far away, that should actually make it a little easier to spot, shouldn't it?
Generally speaking, yes. Because for a part of its orbit, it swings in much closer to the stars, where the geometric probability of a transit is much higher. You get more chances to see it.
Right. An eccentric orbit should increase transit probability, all other things being equal. But, and this is the final beautiful, frustrating twist, this specific resonance, the one that pumps up the eccentricity, it also locks the planet's orbit in a very specific orientation, a state called apsalignment.
This is the final potential layer of the conspiracy, the final cloak of invisibility.
What does that mean, apsalignment?
It means the long axis of the planet's elliptical orbit is locked in orientation relative to the binary's orbit. They precess together in sync.
And the paper suggests that the specific way they get locked is geometrically hostile to us seeing a transit.
The geometry works against us. It aligns things in such a way that the planet tends to be at its closest point to the stars, at a time when the stars are oriented in a way that makes a transit less likely.
So the resonance creates a survivor, gives it a feature eccentricity that should make it easier to find.
And then uses that same resonance to align the orbit in the one way that perfectly hides that feature from us.
That is just, it's almost cruel.
The universe is very, very good at hiding its secrets.
It's like the planet survived the massacre. And as its final act, it pulled on a cloak of invisibility and said, "You will never find me."
And so far, we haven't.
Well, on that note of cosmic hide and seek, I think that's all the time we have for this deep dive.
Keep looking up.
And maybe be a little suspicious of those tight binaries. Thanks for listening. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other podcasts, responding to the content, and checking out our related articles at helioxpodcast.substack.com.